Thank you. Well, I would like to thank you for inviting me to give the seminar here. It's a great pleasure for me to share my research with people, especially with people who have background in experiments, in doing experiments in power electronics. Because personally, I am a theoretician. So I don't do things with my hands. I only do things with pen, paper, and the computer. Yeah? And so, I always value the experiment, and for me, it's especially important what those people who do experiment think about my research, and therefore it's a great pleasure for me to give this talk. So I'm going to be talking about microgrids. Yeah. So my story, as it was already briefly told, is that my background is physics, and as a lot of physicists or mathematicians, I moved towards more practical things, towards applications, and these applications appear to be in energy systems, more specifically electric energy systems. And the microgrids, they kind of represent this very nice field of research, which is both actual in terms of applications and in terms of community, and also very nice in terms of like physics involved. So, here I would like to present actually a pretty big piece of work that was done during the last 3 years overall by a number of people. Well, I'm probably the first author of most of this stuff, but nevertheless, there are really good collaborators of mine here. There were overall 3 different universities involved, although these universities were somehow connected. So, and these universities are, well, MIT, at which I was at that time, during almost all of this time, basically when I was a postdoc. Then Skoltech, and this is a university in Russia, which was created not so long ago, basically 7 or 8 years. It was established from scratch, and MIT was involved in building this university. And then Landau Institute, it's the university in Abu Dhabi, in Arab Emirates. This is also a rather new university, which was also built with the help of MIT. So you can understand why these universities altogether are involved. So because I was with MIT and we've been collaborating a lot. So yeah, so my collaborators are, well, here they are. So the first one is, well, his name is Mike. This is his Chinese name, but his name is actually Mike. He is an engineer. So he was doing things experiment. Now, Mohammed Al-Hasari from Masdar, he is a control scientist. So Sam Chevalier, he is a power engineer. Jim Kirby is, well, he's quite a famous power engineer, but I would say he's electric machinery professor. He's senior professor from MIT. And Kostas Tritsin, he is also, like me, used to be a physicist, and then he became like power engineer. So, and this work is a very good example of collaboration of people with very different backgrounds, leading to some really nice results in terms of theory and practice. So you will judge for yourself. Okay, so this is the outline. Let me just go through because I don't have this remote clicker. So I'll just first I'm going to talk about microgrids. Yeah. So this is like no question. So I'm just going to briefly give you an introduction why we talk about microgrids, why they are important. But I guess in this community, I probably don't need to introduce them for a long time. So then I'm going to show you just on a very simple level what kind of performance we require from microgrids. And this is like nothing too specific, just very basic things. And then I'm going to talk a bit about inverters for distributed generation. And then the main part is actually dynamics and stability. What can we do? What cannot we do? Why? So all those things will be covered there. Then I'm going to present some advanced methods for stability assessment. Or basically, I'll show some nice things that you can do if you use proper models. And then you can write down some nice equations and get some very, very practical results in terms of how you interconnect all of those inverters so that they work together without fighting each other. And then I'm going to give you some nice things about way towards plug-and-play applications. Well, plug-and-play know why electricity is so widespread? Because the power system, the electrical grid, is actually plug and play. So what I meant by that is that if I now plug in my PC to the grid, I just do it. I don't phone the system operator and warn them, please, I'm going to plug in my PC. I'm sending you the dynamic model. Please check that your system will remain stable after I plug in my PC. I don't do that. Yeah, so I just plug and forget. So the power system is actually plug and play in this respect. And this is the reason why electricity is so widespread. So if it wasn't like that, it would have been much more difficult to supply power to different people. And so these concepts of plug and play, they're very important. And unfortunately, if you build a very small systems, very small electric power system, for example, in the lab, it's not going to be plug and play. If you start plugging different things to it, there is a very big chance that you're going to destroy the system. So therefore, if you would like those systems to be scalable, you probably would like to have something like plug and play. Okay, so yeah, couple of standard slides. So in this community, I guess you're all used to it. So conventional power systems were centralized, power flows were unidirectional, load was completely predictable. This is the traditional way of things. That's why actually power systems didn't really see a lot of development, well, in a sense, like technological development in the last maybe few decades, because everything was standard, and they've been just working according to those standard principles. There were no problems with that. And now the new trends are like the distributed generation. Power can actually flow both directions. This is like typically cited, this thing, as kind of a problem. And then flows become highly unpredictable. So these are just very general things. So let's see what does that mean in a more like concrete example. So the standard way of supplying power was like from generation to loads. Yeah? And if you scale the load, if you magnify it, this is the way it works. So this is the conventional representation. So substation, transformer, bunch of loads along the feeder line, and the power flow into them. That's the way it used to be for a long time. So now the new trends that happen, probably especially in US and in European countries, is that people start installing distributed generation. So here I specifically do not limit myself with just PV, so diesel included. Actually, in a certain sense, it doesn't matter in the first approximation what kind of distributed generation. Of course, mostly it's a renewable generation. So, for example, in the southern states of US, especially Southwest, it's very common to install PV because these are very sunny regions. So like California is probably the champion in PV integration, and Nevada is a small state in terms of population. Arizona is also like very extensively using that. So this is quite a popular trend. Now, the next thing is that with the prices for a lot of components going down, people start thinking, okay, let me install storage. So these are famous things like Powerwall by Tesla, like they advertise a lot. These are batteries for just household use. And you can actually afford that. It's just the price of, I don't remember exactly, maybe a few $1,000s, but it's a pretty big 10 kilowatt or whatever unit, which you can use for like more than 10 years. So it could make certain sense, and the price is even going down. So people start installing storage, and then a very natural question. So if I have my own generation and storage, can I just turn off the grid from myself? Can I trip off and live on my own? So this question is very tricky. And the reason is because we've been with the centralized electric supply for so long, we take too many things for granted. So we, as I said, we just plug in and forget. So once you have this, you start having a lot of things that you have to manage. And it's not that easy to do, actually. And I will be describing just one most important thing, which is very easy to understand and very easy to see why it's important. But before that, let us imagine that we did that. And then this part of the grid becomes something that is usually referred to as microgrid. So it's part of the grid that has its own generation, its its own loads and is managed somehow inside. And before we start discussing, let's just, well, this is actually a standard definition, which you can see at Wikipedia, I guess. So let us just ask a question, very basic questions. What kind of things do we need from this microgrid? So suppose I did that, what I would like to have in this microgrid. And these are very basic things. I mean, you don't have to be a physicist or electric engineer to just see those things. So first of all, as I said, this piece of grid should be capable of autonomous operation, which means that if I trip off from the grid, it should be okay. It should be operable. Now, the next thing is that I would like it to be expandable. And what that means is that if I add something, some additional elements, let's say additional generator here, I would like to be able to do that without like completely restructuring the system. So the next thing is that something that is very much widespread in large-scale power systems called N-1 security. What that means is that if I lose one element, I would like my grid to survive. So I would like not to have one single source which is critical for me. Because if I lose a line or something, or the source goes offline, then I would like my grid to survive. So in other words, loss of any element I would like to survive. And then, well, finally, two other, they're not kind of requirements, but I would like to have them. And of course, this list is not exhaustive. We can think about something that looks reasonable from the operational point of view, but these are probably the main things. So the low requirements on communication system, what that means is that I would like my microgrid to work most of the time without excessively measuring and communicating things. Because, well, communication system is yet another system on top of the electric one. If it fails, the electric fails. So I would like to have it simple. And then fast deployment, this is something that I add on my own. What that means is that, you see, in microgrids, it's not always feasible to do very careful preparation to build it. I would like to have some components that I can quickly connect and be sure that they function. So I would like to have this property, because otherwise, in order to build even a small-scale microgrid, I will have to do large-scale calculations before that. So these are the main requirements. And so the one thing that actually comes across all of them, which I'm going to demonstrate now, is that probably the most basic thing that you need is called power sharing. So what that means is that, well, again, I can plug in my components, and then the one fundamental thing that I need from my grid is that the grid responds to variations of my load. So that's a very important thing. I didn't say about it because it's so basic, you don't even have to require it specifically. So, well, imagine a situation, a grid of 3 generators in this case, 3 loads. 2 loads are plugged in and 1 load is being connected at some instant of time. So, well, let me suppose that I say that my first generating unit is responsible for consuming all the sudden variations, and then I measure everything, recalculate and communicate the signal to generators number 2 and 3. And so this is the way it goes. This is the power output of generators as a function of time until my commands reach generators 2 and 3. My generator 1 is carrying quite some load. Well, you can do that, but there are 2 problems with that. The first is communication. The second is that until you send this signal, generator number 1 is actually working at quite some power output. What that means is that you need to oversize it, the first thing. And the second thing, okay, if you suddenly lose generator number 1, your grid is dead. So what you would like to see is this. Okay? So this is nice picture. So they just do it simultaneously. Now, and the question here is, okay, how is it done in large-scale power systems, the power sharing? Well, in large-scale power systems, I have some nice law, which is a Newton's second law, that helps me to do the power sharing. This is actually the main reason why we have AC system and not DC, why it's very, very non-trivial to switch to DC. Well, because in AC you have frequency, and this is a natural physical signal of power imbalance. So whenever you have power imbalance in your grid, your frequency starts to go either up or down, depending on the imbalance size, and you don't actually have to measure all the powers. So what you can do, and it's actually the way it's done now, and the way it was done back there 100 years ago when the grids were just built, is that you only measure frequency at each generator locally. And then you use this deviation to change the power input to the generator. That's called primary frequency control. This is like a pretty basic thing. Well, I guess it's like a well-known thing, but still the interesting thing here is that physics allows you to build completely decentralized power sharing principle. And the way it's done usually is you set your input power dependent on frequency deviations. So this is called droop control. So this is just a simple proportional control. Okay, so, and here is the question that that is interesting when we go to microgrids. And when I say microgrids, I kind of infer power electronics based microgrids. So microgrids that don't have any machines, only inverters. So when we go to microgrids, we don't have Newton's second law. There is nothing rotating in our inverters. So if power changes, inverters do not respond on their own. So this is the way a typical inverter is controlled. Is that like a PV inverter, for example? It just looks at the voltage at its terminal and then decides what kind of current to inject. And the decision is based on a simple principle. You have to inject certain power in your grid, and this power is dependent on whatever power is available from your PV, or if the inverter is equipped with some additional storage, it could be some predetermined power. So this is a very simple, yet by far the most widespread approach. Again, I'm simplifying things. Of course, people who know how to control inverters, they would say, okay, there are a lot of things going on there. PLL, loop, internal voltage, current control. Yeah, of course. But the main principle is this. These are the fine details on how exactly your inverter makes sure it injects the current. But the high-level control logic is this. So your inverter injects current according to this principle. Now, the problem with this is that this inverter is actually incapable of power sharing. So this inverter doesn't see any load variations. It just injects constant power to the grid. It only sees the voltage and decides on what current to inject. Now, another problem is that this type of inverters, you cannot use them to build the grid. You can only plug them into existing grid, but they cannot support the grid on their own because they need this voltage reference. Once they lose the voltage reference, they gone. They trip off. Well, they actually trip off if the voltage variates severely as well. So, what's the way to ensure that you have, first of all, the grid that can live on its own without any external support, and second, that does power sharing? Well, one way of doing that is using some different type of controls, and this control is called voltage source inverter, and it was probably, well, maybe not the first time, but one of the first times introduced and very well discussed in this nice paper, which is more than 10 years old actually. And this is a paper coming from a group of Professor Timothy Green from London Imperial College. This is quite a famous paper actually. It's cited, I guess, more than 1,500 times. And so what they did is they said, okay, there is nothing rotating, but can we just well, actually, what voltage source inverter is that inverter that keeps some voltage output. So instead of injecting current, this inverter tries to keep some voltage at its terminals. Now, but how do you decide on what kind of voltage to keep? So that's the principle. You measure power, and you make a decision on what kind of voltage, magnitude, and frequency you should try to create at your terminal. So sometimes this is referred to as the inverse droop, or well, because the inverter tries to actually support some voltage, it's something that is called master of grid forming mode. Sometimes this is referred to as inverse droop because instead of measuring frequency deciding on power, you measure power deciding on frequency. But this is the way to actually make your inverters respond to power variation. So you kind of artificially create Newton's second law. It's a very nice and elegant way of doing that. So you measure power and you make your inverters respond very much the same as synchronous machines. So an interesting thing is that multiple inverters with these controls are needed for a good microgrid. Yeah, because if you lose one, you would like the others to keep going, and that's basically the requirement. So here is an interesting thing. This paper actually studied, I guess it's only theoretical. Oh no, they had some experiment. Yeah, I remember I was doing a lot of theoretical stuff on this paper. Yeah. So, but this paper just studied one inverter. So an interesting question is that what happens when you've got, I don't know, 100 guys like that? So this is an important question as typical in power systems. People study stability. They say, okay, how do these guys live together? And by far the most important one is small signal stability. Well, why it's the most important one is because if you don't have small signal stability, you cannot function even for a second. You agree just that, yeah? You don't have an operating point. Now, you can have different types of stability. You can have stability in respect to faults, in respect to switching actions. I mean, load switching, not inverter switching. But even if your grid is vulnerable to faults, you still can operate until the fault happens. If you don't have small signal stability, you're dead in a matter of seconds. So, and people study stability, and to do that, you need to consider dynamics of these things. Well, let's do that. So, let me magnify this unit, which is called power controller. Well, in this particular configuration, this power controller is actually a low-pass filter. So what that means is that when you measure powers, you measure P and Q, which are real and reactive power, and make a decision on frequency and voltage. You don't want to see all those, well, measurement noises and all those sudden power variations. So you will filter them. And you put it through a low-pass filter, and you can actually write some nice equations using this power controller thing. And the equations, they go like that. So I'm introducing here inverse group coefficients because it's easier to work with them. It's easier to write equations in terms of them. So the derivative appears because of the action of this low-pass filter. So I mean, I could derive them, but it's just like the length of my presentation doesn't allow to go through all those mathematical details. But this is rather standard stuff. The only thing that I would like to point out here is that if you look at those equations, especially at the upper one, you're gonna notice that it's really, really similar to equations to dynamic equation for synchronous machine. So, and let me just write down the dynamics of a synchronous machine, just to see. So what happens is that if you look at them, they are one-to-one mathematically. So you just have to look at the variables and say, yeah, this is like mathematically, it's completely equivalent. And so here is the question is that if they are completely similar mathematically, maybe the properties are similar. And this actually has been exploited a lot of times. So there is a term which is called virtual synchronous machines. So these inverters are sometimes called virtual synchronous machines. And a lot of people are doing studies on dynamics and stability of these guys, and they base their judgment on this similarity. They say, okay, we know everything about machines. We know how to model them, we know how to study the stability, we know a lot of properties. So, and they just transfer that to inverter-based systems. So, how good that is? Well, let me show you an example of how good that is, and then you'll judge for yourself how good that is. So, stability assessment. So, let's actually ask a very simple question. How stable the system of an inverter working in parallel with an external grid, an inverter being a voltage source. Again, this is nothing bad about a voltage source working in parallel with external grid. It's probably not something that you always do, but there is nothing bad about it. It's just easier to study inverter working in parallel with external grid than to study two inverters. Easier in terms of explanations, not in terms of math. Math is basically the same. So when I study this simple system, it doesn't mean that that's the only system I can do. So all the conclusions, they can be generalized to arbitrary systems. So here is what we do. Let's study stability of this type of inverter working in parallel with the external grid. And I start by writing just the first equation. The second equation is transformed in exactly the same way. So the typical way is done in power systems. I express current in terms of voltage using Kirchhoff's law. I express power in terms of my phase and voltage. Well, here actually, well, this B sinus theta is actually standard thing in power systems, but because I have resistance, I've got additional term with cosine. So these are things that require some algebra, but they're very, very straightforward. And I then linearize my equations. It's also some work with derivatives, and I add to this. Very nice, yeah? It's very nice, like if you forget about those terms, oscillator. Very easy to analyze, very convenient to work with. And so I can do it, what I can do here is I can ask a direct question. What are permissible ranges of my Drude coefficients? Like if I try a point with certain Drude coefficients, is it stable or not? And a convenient way of doing it is plotting something that is called stability region in the plane of Drude coefficients. So here, the horizontal axis is frequency Drude, the vertical is voltage Drude, and I plot the stability region. And the blue region gives me all the points with allowed values of those coefficients in terms of stability. So if I choose this point, I work here, I'm okay. Now, the white one is unstable. Again, I was asking this model about the stability. And now an interesting thing is that what engineers always do, well, good engineers always do, they say, okay, let's check with the experiment, or at the worst case, we don't have the experiment, with the most exact model that we have. Okay? Just to check our calculations. And if you do that for machine, you will see that the stability region that it's happening in real life is very close to the one that you. Now, if you do that for inverter, if you refer to what happens in reality, this is what you're going to see. Now, this is my favorite picture about all this work. Now, what that shows is that you did some calculations which look very reasonable, actually. Because when I was doing that, no one said anything. I mean, you're actually welcome to correct me on the fly if you think that I'm doing some wrong calculations. So, no one says anything when I show these calculations. They look completely reasonable. Everything looks reasonable. And then finally, when they say, okay, let's just be sure. Let's just double check and get something that is not even remotely correct. Now, and this is a very interesting thing because when you have a result like that makes you think, okay, there's something fundamentally wrong with my method. Something really wrong with the way I approach the problem. Because like it's completely inconsistent with reality. Now, along of those calculations, there was some step which was not correct. Somewhere I did something without saying why I'm doing that, and it was not correct. Now, this step is this actually. When I write current as voltage over impedance, I am already using some approximation. I just didn't say about that. And it's very typical in power systems studies to write that. So people just write that silently. I'm doing that all the time without even just questioning that this is an approximation because it's so widespread. I mean, in large-scale power systems, this approximation is so good that people don't even think about it. Now, in fact, this is an approximation. So what I bypass is I bypass the electromagnetic degrees of freedom. Well, we all know about large-scale power systems that there is a very strict division in terms of time scales. Electromechanical, slow phenomena, and electromagnetic fast phenomena. It's really true for microgrids as well. It doesn't matter actually. Because in microgrids, you don't have mechanical, but you have those modes associated with controllers that are also rather slow. And there is a reason for their slowness, and the reason is that it's the way you design those controllers to be slow. You design them specifically to be much slower than the electromagnetic degrees of freedom. Because otherwise, when you measure power, if you measure power which still hasn't relaxed to its quite a steady state value, then your control is wrong. So this division of time scales is still present in microgrids, very much like in large-scale power systems. Now, but why is then I was wrong? Well, that's what I did actually. I crossed this term. Yeah. So that's the equation that I use. So now you might say, okay, what's the problem? Don't cross this term. Just study the system with this term. Well, the problem is that suppose if you have this system. This is an IEEE 123 bus test case. So the problem here is that if I have, let's say, 5 inverters in this system, So if I don't include electromagnetic degrees of freedom, I've got basically 5 oscillators algebraically connected. It's a nice and pretty easy to study system. Now, if I explicitly resolve every electromagnetic transient, I have to write dynamic equations for every line in my system. What that means, if I have 5 inverters in this system, I will have like 200 and something number of equations. That's like really huge step up. Now, I would like to have something as simple as that and as correct as the red one. Well, there is a way of doing that, but before that, let me actually ask a very interesting question: why we need simple models? And this is very interesting. Oftentimes, when you talk to people about model order reduction, they say, "Okay, is your model as exactly correct as the full one?" And I say, "Well, I've got some discrepancies." You say, "Oh no, this is bad. This is just never used." Well, the reason you need simple models is not that you just take simple model and simulate. The reason is that simple models, they allow you to judge on what happens in your system. They allow you to apply some advanced tools, and that's why people like simple models. Well, just an illustration. Well, does anyone know what this is? What this model is? Well, this is a 6th order synchronous machine model with some U control. So you can just look at it. It's a standard representation, like textbooks case. Although, yeah, it's not very easy to remember the whole thing. Now, by just looking at this model, is it possible to judge on whether this model is stable or not? Well, not the model, but the system described by this model. Or in other words, I can tell you, okay, there are some number of parameters here. What are the permissible values of these parameters that allow for stable operation? That's completely impossible to judge from this model. And even if you would like to calculate something, it's like very lengthy and most likely it's just going to be numerical. Now, I can simplify this model by saying that these are fast states, these are subtransient states. These transient states are slow compared to electromechanical. Again, it's a simplification, just an illustration that I did. And I can finally arrive to this nice model, which is an oscillator-like. And now if you look at it, you can just immediately say that this model is stable if those coefficients are, this system is stable if those coefficients are positive. So it's very simple. Well, this is actually exactly what is used by a lot of large-scale power systems operators. They just use very simple models to judge on stability in different areas. Okay, so that's the thing. And how do we approach this inverter system to get something simple and reliable? Well, we would like to have accurate reduced order models, and this is actually this is already my paper. So this was first published a couple of years ago. Now, let me say that me and co-authors, we were not the first one to point out that the electromagnetic transients are important for stability studies, despite their fast nature. But we were probably the first ones to explain why and derive really like these simple models that allow you to see everything. So that's the paper that you can look at. And there is another one which is some nice generalization to already very practical results. I'll show you the content of both, but you're welcome to see for a lot of details. You're welcome to see those papers. So okay, so we need to somehow approach those electromagnetic transients, and the way to do that is to write down this equation and consider this term not as zero, but as some perturbation, some small. And here is what happens. The reason why I do that is because the electromagnetic degree of freedom, the electromagnetic time scale, is, well, depending on your network, it's like a few milliseconds, and the inverter control time scale is decades of milliseconds. Now what I do is I write my current. This is the standard approximation. And this is what I would call zero order approximation. Voltage over impedance. And the next term is this, and let me say it in words, because equations, they're good, but understanding comes when you say it in words. Now, in conventional representation, current depends on voltage and phase. And it just follows voltage and phase. Like that. Now here, current depends not only on voltage and phase, but also on the rate of change of voltage and phase. And now let me plug it back to those equations. and then I arrive to a system like that. Well, it's a bit long, but you see the structure is the same. And now an interesting thing is that what this small correction, seemingly small correction adds, it adds some additional terms which I denote as prime here. Now, you see this model is still kind of oscillator-like, but it contains some additional terms, and I circle in red those that are actually creating those instabilities. So I'll show you in the next slide 2 models, and I'll just show exactly how you can judge that this is the instability. Now, okay, let me just write one under the other. This is very visible. So this is this conventional simplified model. It's actually used in a number of papers. You can see it's pretty widespread, actually. It's not necessarily wrong all the time. I'll tell you how you can judge when it's wrong or when it's not wrong. And this is the model that we derived, which is the corrected model. And you see, so once again, let me just show. So I'll just comment on this one. So if you forget about these terms, if you just consider these 3 terms, it's an equation for oscillator. And the term with the first derivative is friction, if you use the mechanical analogy. And you see that this term introduces kind of negative friction. So it's very, very easy to just judge, oh, okay, I see that this term creates me instability, and therefore, like a very intuitive way of assessing stability is to demand that this whole coefficient and this whole coefficient, they are positive. This is something that I can call stability estimates. And then I can ask questions, okay, what are the most critical parameters of my system that drive instability? How should I change this parameter or that parameter? I can answer those questions by just observing this. Okay, so let me show you how these models actually work. So now this is all different models compared in one picture. Now this magenta line is actually this simple model. So everything here is considered to be stable according to this model. This is the model that I mark as incorrect. Now the green line here is the exact, or you can say it's experimental result. Because when I say exact, people start asking, what does that mean, exact? And the blue one is this model. So you see, by just applying some small, nice correction, we are able to capture all those instabilities, to capture this main phenomenon. So, well, let's finally look at what drives instabilities. And here is where things become interesting, really interesting. Now, again, people study microgrids. A lot of people with experience in power systems study microgrids. And they transfer their knowledge and their intuition from large-scale power systems to microgrids. And they say, okay, I remember I was talking to my colleagues once. We've been discussing collaborative research. And I was telling them that, well, small signal stability is very important for microgrids, and we would like to include that in the work that we are doing. And my colleague responded, well, small signal stability, well, this is some weird thing. This is maybe important for some very long interconnections. We don't see that in microgrids. It's like, why would we need that? So you see, he was completely right in terms of his judgment on large-scale power systems. Really, it's the case. You don't see a lot of small signal instability in compact systems. So you see the small signal stability problems in large-scale power systems when they're very wide. For example, interconnection of Western interconnection of US. Northern states and California is like thousands of kilometers of lines, just parallel lines. But in microgrids, it's actually not like that. So it's very interesting. So let me just use that simple formula, just one of them. Again, it's not exact, but it gives a lot of insight. Let me just write it in terms of droop coefficient and the network characteristic, because I have an analytic formula, closed form formula. I can just write it. So Kp is the droop coefficient. And the stability condition says me Kp should be less than something. And this something is this combination. Now, again, since it's less than this combination, for me, it's better when this combination is big. And let me see. Now, S is the inverter installed rating. R and X are per unit length resistance and reactance of my line. and L is the length of my line. And this is the first thing that I see, is that if the line is longer, it's good for me. That's exactly the opposite of what you have in large-scale power systems. So, in other words, if your microgrid is full of short lines, this is bad. This is really unexpected. I mean, typically people don't comment on that. Sometimes I read papers which are written by people from power electronics. They don't comment on this property. They just say, okay, we created a system, this one is stable, this one is not. And the reason is that typically people who do power electronics, they don't do large-scale systems. And therefore, for them, it's not something unusual. But for people from power systems background, this is really unusual to see. But, well, you can check, of course, that this is true by running direct numerical simulation over a fully detailed model. So these are the results for 3 different lines connecting your inverter to the main grid. So the green stability region is for the longest line. So it's actually a very interesting thing, because the conclusion out of this is the following. Suppose you have a microgrid, which is good and stable. Now, here is the very practical conclusion. It is unsafe to place additional lines in your microgrid. This is completely unthinkable in large-scale power systems. In large-scale power systems, the more lines you have, the better. Well, most of the time. In microgrids, it's completely the opposite. Most of the time, if you have more meshed microgrid, you have more stability problems. So this is really like not trivial, because people, when they have problems with stability, let's say in the lab, they are trying to do exactly the opposite. Yeah? They say, oh, my system is probably like too widespread. Let me make it compact. So, well, another nice, well, you can derive a lot of things based on this formula. I'll just show some comparison with experimental results. But another nice thing is that inverter rating is also in play. Well, what that means is that, suppose you've got a big inverter and you would like to substitute it with a small one because you don't need this large capacity. It could be unsafe in terms of stability. This is just very short but very nice observation. So, well, this is all good, but this is just some theory. Now, here is what I like to show, is that here is yet another paper by the same group, and this is already really, really good experiment. So it's actually 10 years old. I was surprised when I saw that. I saw that after we wrote all the stuff. Now, this paper actually studies exactly the stability of multiple inverters. So what they do is they create this setup of 3 inverters feeding 2 loads connected with lines. Every inverter here is droop controlled the way I described. And then they just, by trial and error, they study where stability is lost, and they just plot a table. And this is the table that describes you the maximum allowed frequency droop, depending on some parameters of the system. So they check inductance, resistance of your lines, distribution of loads. Now, well, believe me on my word, but you can check if you like. But all of this can be described by this analytical. I mean, I can explain every fact by just using this. So this is really good, and I personally very much like it when my results are consistent with practice, with like experimental observations. And here, like back there a few years ago, I've been on this Power and Energy Society general meeting, and I dug into some number of people who do experiments on power electronics. And when I mentioned this nice stuff, like especially with these shorter lines promoting instability, they were saying, oh yeah, we see that at the experiment. So it's really now becoming something that people observe. Like more people start to build those microgrids in their labs, and they start observing those things. And here's actually the explanation. So this is definitely where we were the first. Well, and again, I must admit that we were not the first who said that these shorter lines promote instability. Because before us, there was a nice paper, I don't have a reference here, but I can give it, a nice paper by actually our colleagues from Landau, who established that instability is caused by some clusters of inverters. Again, unlike in large-scale power systems where instability is between remote generators, they said that in some mesh microgrid, the main source of instability are some clusters of inverters, and they derived some algorithm based on some more or less heuristic approach how to locate those. And those clusters appear to be the most tightly connected inverters. So they didn't give explanation to that. And And this is what we did. So we explained also their findings as well. Okay, so now, and here is the question that that we might want to ask, but why? I showed you some results. I commented that they are unusual. The question why? Why inverters are so different? Now, what we've been studying here is that we've been studying how people imitate synchronous machines with their inverters. Now, I imitate synchronous machine, but my virtual synchronous machine appears to be completely not like the real one. So what is special? And we discussed this thing with my colleagues when we actually derived those results. And I said, well, probably the reason is that inverters are typically small, well, kilowatt scale, and machines like 100 megawatts is a big one. And a colleague of mine said, no, I can have a 1 kilowatt synchronous machine, very well synchronized to the grid, just here in the lab, and it's working perfectly. There are no problems with stability whatsoever. And then if you look at the literature on microgrids, inverter-based, inverter-dominated microgrids, low inertia is by far the most widespread thing that you're gonna see. So every time people just say without even explaining, without, you know, like, well, I'm not saying proving, but without even judging, okay, yeah, because of low inertia, microgrids are very much different. You can't model them like, they say, okay, why it's important to include electromagnetic degrees of freedom in your calculus? Well, because inverters are faster, their inertia is smaller. Well, this is not true, unfortunately. It's probably not so nice to say, but it's not true. Well, actually, inertia in inverters is something that I can control. This is actually this controller timescale, this filter. And I can make my controller very slow if I like. It's just the way people just don't like to make them slow because otherwise you lose advantage of your inverters. Inverters are fast by nature, by their nature. So you would like to exploit this fast thing. So why would you physically, like, artificially slow down your inverter more than you need? But even if you don't do that, your effective inertia is still rather sufficient. That's the first thing. And the second thing is that if you increase it, it won't help you. I can have thousands of times difference in between my time scales of electromagnetic and power controller time scale, and it won't help me. This is actually a very widespread question that I receive from people when I talk about these engineers. They say, okay, how fast should those processes be so that we can cross them out? And I say there is no answer. The time difference alone cannot give you the answer. So if it's not inertia, what it is? Now, and here is where things become interesting. It was actually discovered by an accident. Well, of course, you can derive it from expressions, but it's not very easy actually to derive these things just looking at expressions and just start deriving, even if they are obvious. You have to notice them first somehow. And the way we notice them is that I was experimenting numerically with my model, didn't see any instability, and a colleague of mine was experimenting with the model, which he encoded a long time ago, using real-life parameters. And I was using my own parameters. By my own, I mean what I do. I sit with a MATLAB, for example. I code the model. Okay, what would I use for numerical parameters? Okay, I don't want to go to any book and see. I just say, what's reasonable? 1, 1, 1, 1, yeah? In per unit. Well, 1.01, whatever. So you just use numbers that seem reasonable to you. And it's pretty much okay for a lot of it. So I was using some parameters, and I didn't see any instability at all. And I said to him, okay, what's happening? He said, oh, it's unstable, I see. Okay, let's look at your parameters. What are the numbers? And let me proceed, you'll see. So here is a question that I would like to ask. Suppose I've got two inverters that are interconnected by a standard distribution grid line of a length 1 kilometer. These are the per unit parameters, RML, resistance and inductance. The voltage base is 380 volts, which is pretty standard and realistic, and the power transfer from one inverter to the other is 10 kilowatts. Well, one of my colleagues said, well, it's kind of already stupid to transfer 10 kilowatts over this 1 kilometer line. It's a bit too much, but that's okay. It's a bit too much, but this is realizable, let me say. Now, how big is the angular difference in between those two guys? Now, this is the angular difference. It's tiny. It's really, really small. Now, this is an absolutely practical setup in the sense that, okay, you can ask another question. How far should those inverters be so that the angular difference is 1 radian? Well, okay, you judge for yourself. 50 kilometers apart. At least 380 volts and 10 kilowatts. That's quite a lot. So here's what happens is that all the angular differences and also the voltage differences are small in your micro. You can actually understand this at a different angle. So you can ask, for example, a question. The lines here in this room, for example, these are distribution lines. What is the limit power, the maximum power that you can transfer until you see instabilities in terms of angular instabilities? Well, the answer is megawatts. Well, no one thinks about transferring megawatts over those power lines. And the reason is very simple, because until you come there, you reach all the heating limits, you just burn your wires. So with this microgrids, what actually happens is that you typically work, your main limiting factor is just the current rating of your lines. And so you always work at the region of small angles. Another way of understanding it is that if you consider the base impedance for these values of voltage and power, the base impedance is 15 ohms, for example, here. So your line is actually just 1% in per unit. And this was actually the thing that me and my colleague noticed, is that I was using 1 PU as for machines, and he was using 0.01 as for real life. Now, well, and here is the thing is that if you ask the same question for machines, okay, I've got two machines connected using the same line, transferring the same 10 kilowatts. So the angular difference should also be small. Well, no. And the reason is very simple, because with machines, your voltage of the machine is the internal voltage. So you don't connect voltage exactly to the terminal. You connect voltage through an internal impedance of the machine. As one of my colleagues says, machine always hides behind its internal impedance. And this internal impedance is always substantial. There's no way this impedance is small. There is a physical reason for that. Now, and what you can do is you can formally analyze machine in the way we just analyzed inverter, and you will have this instability, but it's going to be in some crazy region of Drude coefficients, which is never used in practice. So the reason is that it's just like completely unreasonable value. Well, 55% for this case, but it's even very conservative, I would say. Okay, so yeah, let's then go to some. Now we're gonna go a bit quicker because I'm gonna describe some practical applications. The math behind is more cumbersome, and there is no need to analyze it in like more details. So so what I was showing you is just an explanation of what happens. Now, it's good, but it's much better to have some really solid practical applications. And here they are. So the generalization to multi-inverter case is very simple. So we can generalize our modeling approach to arbitrary networks of inverters. So all your variables become vectors, all your coefficients become matrices. And the only nice thing that I would like to point out that all the matrices in your equation here, the ones that are coming from the network, they are finally coming from an admittance matrix. An admittance matrix has this nice property. If you remember this, like it's not easy, kind of. If you didn't try this stuff a lot, it's not easy to keep in mind this property. And the property is that every term in your admittance matrix is only from one line. Yeah? All non-diagonal terms, they are only coming from one interconnecting line. If there is no line, the term is zero. Yeah? And what that means is that actually I can split my admittance matrix into parts, and only one line is responsible for one part. This is going to be important for the second part of my talk, actually, the one that I presented in this American Control Conference. Because this nice property of admittance matrix allows you to do really magical things. So now even for this system, I can do this. I won't go into much details, but I would like to point out some rather interesting thing. So what is the big advantage of having this simple model like that? What is this? This is a linear model, which I can call coupled oscillators. Now, what is the advantage of having this model? Well, apart from the fact that I can look and see, oh, okay, I approximately understand what drives my system. Okay, good. I understand it, and that's it. Yeah? But what is the main advantage is that with this model, it's very easy to play in this advanced stability assessment case. By advanced stability assessment, I mean I can do some nice things and come with some conditions. I can, well, basically, there is this method of doubling functions, yeah, well-known thing. Instead of directly assessing, you construct some combinations, prove that they decay, and you certify stability. But the problem is that construction of these combinations is very tricky and like difficult thing for arbitrary systems. Now, what linear system and especially this linear coupled oscillator system allows you to do, it allows you to construct those combinations like in a rather general way. And unless you are completely unlucky, those combinations will be reasonable. In other words, it's like, suppose you've got a system of 3 or 4 connected oscillators. Instead of proving stability by looking at the eigenvalues, you can look at how the energy of the system behaves. So you can say, okay, what happens to the energy of my system? If the energy is decaying, then the system is stable. If the energy is not decaying, well, I mean, the system can be subject to external disturbance. Okay? So if the energy is not decaying, then the system is not necessarily stable. And if you don't know the expression for your energy, you can guess. Well, I know that my energy is velocity squared plus coordinate squared with some coefficients. Well, I can guess. I can just assign some coefficients, and unless my system is very unsymmetric, this will give me approximation. So the same thing can be done here. So we can come with some nice Lyapunov functions. I just omit the details. So the way it's usually done, the Lyapunov functions are quadratic. Well, the quadratic Lyapunov functions are quadratic forms. Yeah? So this is the way it goes. W is the Lyapunov function, U is the decay rate, and finally, for stability certificates, all I need to show is that both are positive definite. That's very simple. Well, again, that's very simple principle. There is some algebra involved. Now, and now here is a tricky and interesting thing that comes here. Is that what is typically happening in control theory is that, okay, we've got Lyapunov function, we show that it's decaying, we certify stability. Now, and here I am being a hardcore practical engineer. I'm saying, well, okay, I will prove that, I will write some expression which says this matrix is positive definite. By the way, this matrix, this P, is not 3 by 3 by 3, because every block here is block. And the block is n by n, where n is number of inverters in my system. I've got 100 of inverters, this matrix is 300 by 300. Okay, I can probably try and find values for my parameters for this matrix is positive definite, but what good does it do? Now, here, being an engineer, I would say, can I somehow derive something really simple, again, out of this? Well, I can, if I look closely at this matrix and I use this nice property of admittance matrix that I'm going to split it. What I can do is I can, well, these are the mathematical conditions for Lyapunov function and its decay. So now, it's possible actually to use this, exploit this nice property of admittance matrices to split both P and Q, which are the matrices for Lyapunov function and decay, into components, each one coming only from one interconnection in your system. So this is just sum of matrices, each one is from one of the components. From one of the interconnections. And then demand positivity for every term here. This is going to bring you some additional conservativeness, but it brings you quite a lot of convenience. So, well, what that leads to is that you derive it for every term and you get simpler matrices. Here, this one is, these blocks are 2 by 2, so this one is 8 by 8. And it's very easy to certify the positivity. You just, again, look at these blocks. Again, this is just algebra, which is, well, cumbersome, but not difficult. So the final result here is the following. So I can arrive to a set of stability conditions, to a set of algebraic equations. Each equation is related only to one interconnection. So I take every line in my system, which connects two inverters, and I write one condition for this line. How many lines I have? That's the number of conditions times 2 actually, because frequency and voltage. Here I only show for frequency. So for example, for this system, for interconnection between I and J, this is the condition that should be satisfied. These are the two coefficients, n is the total number of neighbors, s is the rating of the verb, and this is the line in between those intervals. Now, this is a very practical result, actually. Suppose you're applying a microgrid. You assign some values for, well, you have some lines, you've chosen the lines, and you want to assign some values for your groups. And this is a very fast way to check stability. You just write down these things, you can just do that. And you just check. And if they all satisfied, then I guarantee that the system is stable. If they are not satisfied, then you see which ones are not satisfied. So now, if your initial design was not completely unreasonable, then most likely what's going to happen is that just few are not satisfied. If all of them are not satisfied, well, what that means is that probably you've chosen not a very good way to design your microgrid. That does not necessarily mean that it's unstable, because these are conservative guys. But that could mean that probably stability is questioned. So, and if you see that some of them are violated, you just correct them. Well, how you correct them? You tune your groups of just these intervals, just these two for which this is violated. Not at all of them. Yeah? So, well, but this is just one application, because there are other ones. Because you see, since it's completely decentralized, now suppose I'm just, I have a practical situation. I have a microgrid that is perfectly functional, and I would like to connect additional verbs. Well, let me imagine like future power systems. Every neighborhood has its own microgrid, and I am building my own house, and I'm connecting it to yet another neighborhood. And what I'm gonna do, like if I don't have these kind of methods, what I would need to do is I would need to go to this neighborhood, take all the dynamic model, incorporate my house, certify stability, and then connect. Now with this, what I do is I need only the information about the connecting point, the terminal, the nearest neighbor. I just ask my nearest neighbor, excuse me, how many neighbors do you have, and what are your group settings? He says me or she says me, and then I connect my inverter. I write down additional equation. I judge on how should I tune my coefficient. If I need, I can ask my neighbor, please reduce your group to something like that. Very, very simple, and yet very practical. Actually, for those of you who are familiar with optimization theory, you can see that I like to pronounce this. These conditions, they actually correspond to a convex set in the space of group coefficient. Now, those of you who take classes on optimization theory already know what that means. So it's a piece of cake for optimization. Yeah? So this is really, really convenient. So, well, a lot of possible applications, like interconnection under limited observation. That's the thing we like. Limited information about the system. This is typical for microgrids. Okay, so let me proceed. Oh yeah, this is just an example for 3 inverters, and this is the picture that shows how conservative we are. So the blue is this our prediction, and the red is the real stability boundary. So you see, surprisingly, we are not really very much conservative. This is actually very important, because oftentimes you derive some Lyapunov stability things and you are conservative. Okay, so let me then probably, because I have another part on small part on plug and play, I'll just skip it, and we can actually make a short break, 5 minutes, because I'm talking for more than an hour already. You must be tired. So we can make a break for 5 minutes. Maybe you can ask questions about this first part, and then I'll show you this like another approach, exactly the one that I showed at the ACC conference after the break, and I'll have a chance to drink my coffee. Explanation, I'll just refer you to the papers. We actually generalized the results that you just saw to something that is completely plug and play. Completely plug and play in the sense that you tune your inverters in a certain way and you connect them and they're stable. So these are the 2 papers that you can look. They kind of explain what happens mathematically. Now, the problem here, even with these results, with plug and play, is that we still stick to one way of controlling an inverter. So these nice results, yeah, but they only work for one type of control the way I described. Once you have components with different dynamics, you will have to generalize the theory to something else. So let me now present you this more or less recent results that actually can generalize the whole thing. And you can then use those results to certify stability for complex systems with absolutely arbitrary components. So now, well, this is what I call the centralized stability certificates for arbitrary networks. So this is the paper that is actually related to this, the one that I actually presented at the just past American Control Conference. Now, this is actually very much related to a paper which is 20 years old. And this is a hardcore paper in control theory, which is dedicated to integral quadratic constraints. So, well, it's written by Alex Medvedsky, which is by chance Russian as me. But this is not the reason I... Actually, this my ACC paper, when I was writing it and driving all the things, I didn't read this paper by Alex, not at all, because this is way too hardcore even to me. I mean, well, I can read it, but actually using it, it's not very easy. But this is much better because this approach is much more general. But I will just present you an explanation of this approach, which is very simple, but it's limited to linear systems, though. And again, he was referring to arbitrary systems. It's like a control theory. But I am referring to specific electric power systems because they've got these nice properties which we can use and we can arrive immediately to some practical results. So let me start by just reconsidering what they were doing and giving it a bit different language. So now, let me suppose that I have a system, a dynamic system, with multiple inputs and multiple outputs. Well, this is a typical approach in control theory. Now, for a converter or a synchronous machine, it doesn't matter. The inputs are variations of voltage, and the terminals and the outputs are currents that are coming out of it. So it's very simple. You vary voltage, and you see some current response. So now, let me also assume for my system that the number of inputs and outputs they are equal. So I've got two components of voltage and two components of current, for example. Well, you can have three phase, or two, it's transformed to DQ reference frames. Now, so in linear approximation, there is a general way of connecting your inputs and outputs through a transfer function, which is in Laplace space as a function of S, with frequency domain, yeah, if you want. Again, the model can be arbitrarily complex. It could have numbers of internal degrees of freedom. It will just mean that the G has higher order. The only thing is that it's linear, but the internal complexity is not linear. Well, there are some rather mild conditions on this model, which I don't want. So now here is an interesting thing is that the key to deriving this nice stability thing is that look at the system dynamics when there are no inputs. So by inputs, I mean some perturbations. So what happens to your system outputs when there are no inputs? Well, your system outputs live on their own. And they live according to this equation. Now, what that means is that not any output can be realized in this system. So your outputs have to satisfy certain condition, and the condition is that the determinant of this transfer function should be 0. Only then you can have non-zero y's in this case. So what that means is there are some number of natural modes of your system. Now, and the conditions for existence of these guys is that the determinant is 0, and there are some number of roots of this determinant, which is equal to the number of states in your system. And so the stability condition says that the real part of every root of this equation should be negative. What that means is that every eigenmode is decaying in time. Well, this is simple. This is way too simple. This is first or second year dynamic systems material. Yeah? So now, but this opens the door to formulate some nice stability condition. well, actually, you can check stability directly, but you see, the problem is with the determinant. Okay, so here is an interesting trick that I can do. Let's suppose that I'm considering some system which I call real system here. And I would like to certify its stability. And let me do the following trick. Let me change my system somehow to the point when I know that the system is stable. For example, for power system, I can scale down all my loads. This was a very popular approach in voltage stability studies, for example. You scale down all your loads, then you have a solution for voltage, and then you just gradually build your load up and see what happens. It's not the same here, but it's just the way you change it, it's up to you. Let me just say that I've got some parameter which describes this change, and I call it alpha. So alpha is equal to 0 for definitely stable system. When I know that the system is stable, say empty network, it's stable. And alpha 1 means I'm plugging in all my components. And alpha just the coefficient that describes the power of a component or some control parameter. And now let me do the following thing, is let me plot those roots of the determinant as alpha changes. Now when I start from a definitely stable system, these roots are here, where it should be. So I'm plotting 2 roots, but they can have 200, doesn't matter. And now when I grow my alpha gradually, my roots start to move. And now if finally my system is unstable, then my roots appear here. But somewhere in the process, at least one of my roots necessarily crosses the imaginary axis. If the final system is unstable, it must happen somewhere. And now here is the condition that I can write, is that the determinant as a function now of omega, not of complex S, just one real variable, is not 0 for every alpha going from 0 to 1. So what that means is that no one of those guys ever crossed the imaginary axis. Now, well, that's still kind of hard because of determinant. But let me now say that I'm substituting this condition with another one. Instead of demanding the determinant being on 0, I demand the positive definiteness of this matrix, G plus G condition. Now, what is good about it? Well, first of all, this is conservative, yeah? So determinant is non-zero, but the corresponding G plus G condition does not necessarily have to be positive definite. However, if it's positive definite, there is no way determinant can ever be zero. Now, what is good about this is that the determinant condition is not additive, but the positive definiteness is additive. In other words, if I have system with a G matrix, which is a sum of 2 different matrices, each coming from one subsistence, one of the subsystems, then the determinant of a sum is an ugly thing. It's just nothing. But the positivity is conserved in the sense that if I say that G1 is positive definite, G2 is positive definite, then G12 is also positive. Well, this property is sometimes called passivity, actually. Now, the systems that possess this, they are called passive. And it's well known, like interconnection of passive systems is passive. Well, not every interconnection, but feedback interconnection, or parallel interconnection of passive systems is passive. Well, there is one problem with that, but nevertheless, let's see how it all related to power systems. And this is actually where things become nice. So here is an interesting thing is that, as I showed you before, I can write down equations for power system dynamics and linear approximation through the use of this admittance matrix. And this is the key of using these nice conditions. So, and the reason is that my admittance matrix, here is what I can do. You see, the 3 by 3 matrix, I can spread it into a sum of 3 matrices. Each one has only 4 non-zero components. Now, actually, it's a bit trickier than that because every component here is also a 2 by 2 matrix. So it's a bit of nice algebra, but it's just a bit. So you see, and now, if I, for example, have a way of showing positivity for just one of those parts, well, together with loads, then I can scale it up to networks of arbitrary size. In other words, what happens here is that I have a tool to define stability completely locally. So by exploiting the properties of this admittance matrix. So let me show you, just add some components, some loads to this matrix, and you'll probably see. So here is like the way the equations are written, like what are these currents, I1, I2, I3, these are currents going into your nodes, into the nodes of your system. And V are the voltages. But an interesting thing is that the current that goes into the node, it goes through your device that is connected, being a load, a generator, whatever. And you can kind of generalize the whole thing. And you can, but before showing the generalized version, let me just quickly state the formal things. So I'll just remind you, sorry for being sloppy a bit. So we're working in small signal stability. Yeah? So we use, because I showed you admittance, but it's actually like full scale, 3-phase AC network. Yeah. So we use phasor representation, then we expand, we use small signal framework, and then we go to frequency domain. So just a bunch of standard stuff. Because sometimes people, especially power electronics people, they say admittance in the frequency domain. They already know what they mean. This is what they mean. So for example, every component can be described like, okay, current in, depending on voltage, is Y, I is equal to admittance times V. So this is called input admittance. In general form, the input admittance is matrix, because your current, well, you can write it in like 3 phases or in DQ frame. Well, I assume that you at least know what DQ means. Yeah, it is just a transform to different linear representation of your currents, excluding your, it's actually phasor representation. So, well, for example, just a simple example. This is the way line looks on this admittance language. If I have a line which is short circuited to the ground, what is the input admittance of this line? Is this matrix. So you see, it's kind of impedance, yeah, but you see there is this part which is dynamic. What that means is that I am resolving electromagnetic again here. So this is the line admittance. And admittance for other components are going to be something like for a machine, you can have an equivalent admittance. It's going to be a bit ugly though. I showed them the day before yesterday at PSGM. And even for simple model of machine, it's kind of big formula. But the good thing is that you don't need to write them by hand. Yeah? All you need is the framework. You need to understand that every component is 2x2 matrix, admittance matrix, and every line is 2x2 matrix like that. And then all of them, they are assembled together in this big admittance matrix, which you can then split upon. That's it. So it's some algebra. So in other words, here is the way it looks. So the network admittance, this is the admittance of your network. It's just exactly that I showed. And the lowered admittance, this is just diagonal matrix. So your lowered admittances are on the diagonal. And your equation for voltages, for node voltages, well, to be precise, for node voltages variations, is this. The full Y times V equals 0. Which means that there are no external currents coming to the nodes of my V. All the currents, the current that goes to the node, go through my load or generator. It doesn't matter, yeah? Because this admittance matrix is there. So this is the equation, and this is the equation exactly that we have. G times V equals 0. So now all I need to do is I need to apply this technique to this Y matrix. So all I say is that this piece of matrix should be plus its Hermitian conjugate, should be positive there. That's it. So now, and every piece actually here in the network admittance matrix is this 2x2. So again, what is important is that everything is splittable into these very small pieces which are easy to analyze. And then you analyze just one. You analyze a line plus a load. And if it satisfies certain conditions, then infinite number of these guys connected together in arbitrary way are stable. Okay, so let's do that. So before that, I'll show you what is the admittance matrix for an inverter like that. So you can use these dynamic equations, the ones that I showed before, with different notations here, to calculate the effective admittance matrix. So it's a line plus an inverter, and then the ground. So you see, it's a bit complex, yeah? So it's not that nice. And this is even for a very simplified version of this inverter, because I already made some assumptions that the angle is small and all this stuff. If I use a full-scale model, I won't even be able to show it on one slide. But I will be able to plot a lot of things. So now this is the admittance matrix for node minus 1 here. So if I show the formula, it already doesn't fit the slide. So here is what happens is that, let me now check the stability. So again, according to what I just said, is that I need to certify positive, basically positive definiteness of this plus its Hermitian conjugate. And I can do it numerically. So here is what I do. I take this matrix, which is inverter plus a piece of line, and I ask a question, what are the eigenvalues of this combination? Well, here is the plot of eigenvalues. They are in red. Now in blue, the eigenvalues of just a line. In other words, here is what I do. I take a load, which is, load component line plus inverter, and I ask the eigenvalues. And then I compare it with just a line. Now, why would I do that? Is because, as I said, if I scale down the inverter, it's just a line which is perfectly stable. And so this is exactly what I see. The eigenvalues for this admittance matrix that is corresponding only to a line, they are positive, which means that number of lines connected to a network is stable. Well, congrats, nice result. Now, what it shows also that if I connect inverters, that I cannot say that they're stable because I see some negative eigenvalues. So here, and well, actually, what you can do is you can play with the inverter parameters and try and make these eigenvalues positive. And this would mean that you, I guess this is called passivation of your system, something like that. So you make it passive. So you can do it. But the problem is that in order to do that, you will have to change your control parameters to such values which are completely impractical. Now, here is an interesting thing is that, and it's actually the idea behind is in this integral quadratic constraint paper, but it's written there in such a way so that it's not very easy to find. So now, let me take an initial stability condition. Initial stability says not that y plus y Hermitian should be positive, but the determinant is not zero. And what that means is that, what if I first multiply this matrix by some other matrix, which is non-singular, and then demand the positivity? So again, well, this is sometimes, this kind of approach sometimes is called passivity multiplier. It's actually not exactly like that, but it's just think about it as a mathematical tree. Just don't think about it as kind of a known tool. Just a mathematical tree. Suppose you're doing mathematical exercise. Your initial condition is what determinant y not zero, and you say this one is not good. Okay, let's just try different matrices. Let's just try multiplication and demand positivity for this product, and just see what happens. And actually, an interesting thing is that what I would say is that if I try different m's, I will make the system look passive. That's the term that I use. So here is what happens. So let me choose this m. Now, this actually has a very nice interpretation. The positivity of y plus y Hermitian has an interpretation that the system is consuming real power. You can think about it like that. Now, this matrix M gives you another interpretation. The system is consuming reactive power. Again, for stability purposes, it doesn't matter, because if your system is consuming reactive power, that means that your currents and voltages cannot go infinite. Therefore, your system is stable. And so if I choose this matrix, which is non-singular, as you can see, and plot the eigenvalues of this, here is what I get. So you see, now they look very nice at zero. So your inverter is actually passive in this representation. The only thing is that I can tell you is that, I must tell you, is that, of course, I've chosen the parameters so that this eigenvalue touches zero. But now these parameters lie in a very good region. So it's reasonable. All my pictures are plotted using values that are completely reasonable for real life. All of the pictures throughout the presentation. I never plot pictures which use values that are orders of magnitude way off the real life. So that's just a remark. So now, here's what happens is that you see this, okay, It's nice near zero, but the problem is here it's negative. Okay, so what to do? Well, what to do is a very simple thing. Is that if I plot again, the initial one is this. But no one tells me that M cannot be piecewise. There is no such requirement. Well, besides, I don't even have to have a piecewise M because I can transition them from one to another. There are many ways of doing it, using some sigmoid functions. But piecewise is perfectly fine. I mean, what I do is I choose M to be just unit for big frequencies, for large frequencies, and M to be this one for small frequencies. That's it. So this is a very easy thing. Now, this is just like a nice illustration on one type of components. But you see, an interesting thing here is that I can split my frequency range into any number of pieces where I like. And I can split them according to what I see in my devices. So I take every device in my system, and actually the number of devices is limited in the sense that the number of types of components is limited. So every group control inverter is going to look similar to this one. You can plot transfer functions for synchronous machines, for current source inverters, and they all have some distinct shape, and every component with this type of settings is going to be similar. So at the end of the day, if you ask yourself how many types of components are there in electric power systems, not too many. So most of the current source inverters are tuned in like the similar way. And then you plot these things, and then you see exactly where in the frequency domain you got problems. It's like very much the same I see here. I see the problems at the low frequencies. And then what you can try to do is you can try to choose these matrices M actually separately for every piece of frequency domain in order to satisfy all the components. And then you can even solve it as an optimization problem. If this problem has a solution, then it's okay. If it doesn't have a solution, then that means the system is unstable. Well, most likely. And then that means that you can try and choose different control settings for your components. And finally, what you can do is you can identify the problematic pieces in your frequency domain, where your components tend to be unstable. And it's much easier to correct. And why it is easier to correct? Well, I don't show it on the slides here, but I've done this mathematical exercise. Now, you see, if you look here, you see that the problem at very small frequencies. This is written in per unit, yeah? It's very small. Now, a very nice thing is that when I have something like that, in physics, say I have a small parameter. Now I can expand all of my expressions in power series of this frequency. And I can write analytic formulas. For example, the matrix that I showed you, the Sunday one, I can expand it. And I write analytic. I can write even analytic expressions for eigenvalues. And once I've done that, I can see what happens. And I can see how they are dependent and so on. So it's like, this is just a framework. It allows to do a lot of things actually. The only thing is that there are a lot of calculations involved. It's just some analysis involved, but this analysis is a very guided one. So in other words, you plot it, you consider, you see where the problem is, you expand, and you see the main parameters that actually govern this. So that's basically it, I guess, with this second part. Yep. So this is the whole thing. So we started from inverters, considered why they are unstable, showed some nice things, finally we generalized it. So I hope the next time I will show generalization to all the components. Well, basically, yes, this is actually the way to building completely plug-and-play microgrids in the sense that specifying exactly which type of control settings to avoid for microgrid components. Well, the only thing is that this analysis is linear. Yeah? But that's okay. It's a small signal stability thing. For non-linear, well, actually, the original IQC integral quadratic constraints, it allows approaching of some non-linear components. But this is some additional work on how to generalize that to non-linearities. Okay, yep, that's basically it. So these are the publications associated with this talk. These are acknowledgements. I must show them. Yeah, this is, thank you.